The universe is hiding most of itself from our eyes. For decades, astronomers have known the cosmos holds a profound secret, that the galaxies and stars we see are just a glittering sprinkle atop a vast, invisible ocean of something else. This missing mass shapes everything, yet it refuses to shine, leaving us with a cosmic map full of blank spaces. But what if we had a tool that could trace the outline of the unseen by using gravity itself? That tool exists, and it was predicted by Albert Einstein over a century ago. It is called gravitational lensing, a natural phenomenon where the gravity of massive objects bends the path of light like a cosmic magnifying glass. By the end of this exploration, you will understand how this single idea allows us to map the dark matter scaffolding of the universe and observe galaxies from the dawn of time. We will see how light, warped by invisible mass, reveals ghostly halos around galaxies, illuminates the filamentary web of creation, and even helps us find hidden worlds. What do you believe is the most profound thing we can learn by seeing the unseen? For most of human history, light traveled in a perfectly straight line. It was the ultimate cosmic rule, a beam from a star or a lantern cutting through the emptiness with unwavering certainty. Our maps of the heavens and our very understanding of reality were built upon this simple, trusted fact. Then came Albert Einstein, and with him, a revolution in thought so profound it reshaped the cosmos itself. In his theory of general relativity, Einstein proposed a breathtaking new vision. Gravity, he said, is not a mysterious force pulling across distances. Instead, it is the geometry of the universe. Imagine space and time not as a static stage, but as a flexible fabric, a vast, invisible trampoline. When you place a heavy object like a star or a galaxy onto that fabric, it creates a deep, smooth dimple. This curvature is gravity. Now picture a beam of light, that faithful straight-line traveler, passing near this cosmic dimple. It does not get pulled, it simply follows the curve of the fabric. From our distant, flat perspective, the light's path appears to bend. The star is not where it seems to be, its image subtly shifted. This was the prediction that mass could literally warp the path of light. It was a staggering idea, suggesting the universe's stage itself was malleable, and that the most constant thing we knew, light, was willing to follow its curves. To grasp gravitational lensing, you must first accept this beautiful, counterintuitive truth. Gravity is not something that happens in space, it is something that happens to space. And everything moving through it, even light, must go along for the ride. This elegant idea, however, seemed destined to remain trapped on the page. Einstein himself, after publishing the mathematics of general relativity in 1915, saw the implications for starlight. His equations clearly showed that a massive object could bend light, acting as a lens. Yet when he contemplated the practical reality of observing such an effect from distant stars, he dismissed it. To him, it was a fascinating theoretical curiosity, a beautiful consequence of his new theory of gravity, but one so infinitesimally small that no telescope of his era, or any he could foresee, would ever detect it. He famously wrote that there was no hope of observing this phenomenon directly. The cosmic dimple was too shallow, the deflection of starlight too tiny to measure, or so he believed. The universe, it seemed, was not ready to reveal this particular trick, but science has a way of surprising even its greatest architects. The first crack in this skepticism came not from a distant galaxy, but from our own sun. In 1919, just a few years after Einstein's publication, the British astronomer Arthur Eddington led a daring expedition to a remote island off the coast of Africa. His goal was to test a critical prediction of general relativity during a total solar eclipse. the moon's shadow would blot out the sun's overwhelming glare, allowing astronomers to photograph the stars that appeared right next to it in the sky. According to Einstein, the sun's gravity should bend the light from those stars, making them appear slightly out of position compared to when the sun was elsewhere in the sky. Eddington's meticulous photographs revealed a tiny shift, a minuscule deflection that matched Einstein's predictions almost perfectly. The news shook the scientific world, catapulting Einstein to global fame. This was the first proof that light could be bent by gravity. It confirmed the warped geometry of space. While this solar deflection was the most subtle form of lensing, far too weak to magnify or distort images, it proved the principle. The cosmic trampoline was real, and light was indeed riding its curves. A door had been nudged open, revealing not just a validated theory, but the faintest glimpse of a future where we could use gravity itself as a telescope. Eddington's eclipse was the first whisper, proving light could be bent. But to truly become a cosmic tool, this bending needed to be far more dramatic. The key lies in the scale and alignment of the universe's actors. To understand the powerful lens, picture a simple, everyday scene. You are standing in a dark room, looking at a bright candle flame on the far wall. Now hold a wine glass between your eye and the flame. Look through the curved base of the glass. What do you see? The single flame is distorted, perhaps split into multiple ghostly images, stretched into a shimmering ring of light. This is the perfect analogy for a gravitational lens in space. In this cosmic setup, the bright candle flame is our distant light source. This could be an incredibly luminous quasar, the blazing core of a young galaxy, or any brilliant beacon from the far reaches of the universe. The curved glass is our massive foreground object, a galaxy, or even better, an enormous cluster of galaxies. Their immense collective mass creates a profound dimple in the fabric of spacetime, a deep, smooth warp. And you, the observer, are here on Earth, looking through this natural cosmic lens. Here is how the magic unfolds. Light rays stream out from that distant quasar in all directions, traveling for billions of years across an expanding universe. A few of those rays happen to pass very close to our massive galaxy cluster on their journey. As they skim the edges of this immense gravitational dimple, the warped spacetime forces them to curve. These bent rays then continue on, now on a new path, converging toward our telescope. Crucially, light from a single point on the quasar can take multiple different paths around the lens, all curving by different amounts. When they finally reach us, our instruments do not see one quasar. We see 2 or 4, or even a perfect circle of light, all mirage-like images of the exact same object. This is an Einstein ring, the most elegant signature of lensing, where the alignment is so perfect the images merge into a halo. More often, the alignment is slightly off, and we see spectacular, stretched arcs of light, like smeared brushstrokes across the sky. These arcs are not new galaxies. They are the grotesquely magnified and distorted images of background galaxies, pulled like taffy by the gravity of the foreground cluster. In every case, the lens itself, that massive galaxy cluster, remains largely invisible in this optical dance. We see its effects, not its substance. It is the hidden hand that rearranges the light of the cosmos, and by studying these ghostly rearrangements, we can finally map the hand itself. The most spectacular proof of this cosmic lensing is written across the sky in arcs of light and perfect circles. When the alignment is just right, when a brilliant background galaxy, a massive foreground cluster, and our telescope fall into a near-perfect line, gravity performs its greatest trick. This is strong gravitational lensing, and it transforms our view of the universe into something from a dream. Instead of a single, faint smudge of a distant galaxy, we see it replicated. A single quasar might appear as 4 identical copies, arranged like celestial guard posts around an invisible center. The light from that one object has taken multiple different paths around the gravitational well, each path bending by a different amount before all converging at our eye. When the alignment is absolutely precise, these multiple images merge into a single, stunning ring of light encircling the lensing cluster. This is an Einstein ring, a halo of warped reality, and it is one of the most beautiful and conclusive signatures in all of astronomy. But what creates these rings and multiple images? It is not the visible stars of the foreground cluster alone. The gravity required to bend light so severely is far greater than anything the cluster's glowing stars and gas can provide. The lens is overwhelmingly powered by something we cannot see, the immense halo of dark matter that swathes the entire cluster. Those graceful arcs and perfect rings are, therefore, not just pretty pictures. They are direct qualitative proof of concentrated invisible mass. They are the outline of the hidden hand traced in fire. We see the effect, and from that effect, we know with certainty that a tremendous, unseen gravitational force is there, sculpting the very light of the cosmos. It is a cosmic neon sign pointing to the dark scaffolding of the universe. But these spectacular rings and arcs are the rare cosmic jackpot. For every one of those perfect alignments, there are millions upon millions of more subtle interactions happening across the sky, a quiet, universal warping that is invisible to the human eye. This is the realm of weak gravitational lensing, and it is here that the true power of this technique unfolds into a precise scientific instrument. While strong lensing gives us stunning portraits of individual dark matter clumps, weak lensing allows us to map the entire cosmic landscape, the gentle hills and vast valleys of the universe's gravity field. So how does it work? Picture a field of distant spiral galaxies, each one a delicate, spinning pinwheel. Now imagine a vast, invisible sea of matter lying between them and us. This could be a diffuse filament of the cosmic web or the outskirts of a massive cluster. As the light from each of those billions of pinwheel galaxies travels through this sea, it passes through regions of slightly warped spacetime. Each individual galaxy's light is bent by a minuscule, utterly imperceptible amount. Its image is distorted just a little, as if seen through a faintly flawed windowpane. The key is that the distortion is coherent. All the galaxies behind a particular patch of invisible mass will be stretched in a similar direction, their shapes very subtly aligned, like iron filings responding to a magnet you cannot see. No single galaxy shows a clear sign. Its natural irregular shape masks the tiny effect. But by studying the orientations of millions of galaxies across a huge swath of sky, astronomers can perform a statistical detective act. They can measure the systematic collective warping of the entire population. It is like listening for a single quiet note in a roaring concert hall by analyzing the hum of the entire crowd. This statistical signal, this whisper of aligned shapes, is the fingerprint of the intervening mass. By measuring it, we can create a map. We can chart where gravity is slightly stronger, tracing the distribution of both luminous galaxies and, more importantly, the diffuse dark matter that connects them. Weak lensing does not give us a pretty picture of a single arc. It gives us a data-driven census of the universe's hidden skeleton, allowing us to weigh galaxy clusters, measure the growth of cosmic structure over time, and even probe the nature of dark energy itself. It turns the entire sky into a canvas where invisible mass paints with the faintest brushstrokes of distorted light. But the universe's hidden structures come in all sizes, from the vast cosmic web down to solitary wanderers drifting between the stars. To find these lone, dark voyagers, we need a different kind of gravitational eye, one sensitive to the briefest of whispers. This is the realm of microlensing, where the lens is not a galaxy but a single star, a planet, or a black hole. Here, the cosmic alignment is so fleeting, and the lens so small that our telescopes cannot possibly see multiple images or arcs. the separation between the warped light paths is smaller than a pixel in our most powerful cameras. So if we cannot see the distortion, how do we detect it? We watch for a telltale flash in the night. Imagine a single, distant star shining steadily in the galactic background. Now imagine an invisible, compact object, like a solitary black hole or a rogue planet with no sun, drifting silently through the void. By pure chance, this dark lens passes almost directly between that background star and our telescope. As it moves into alignment, its gravity acts as a tiny, natural magnifying glass, focusing the star's light rays that would normally spread out. For a period of days, weeks, or months, the background star does not split into images, it simply grows brighter. It peaks in intensity when the alignment is perfect, then fades back to its normal glow as the lens moves on. This temporary brightening is the signature of microlensing. Its unique power lies in its democracy. It can detect anything with mass, regardless of whether it emits light. This makes it the only method we have for finding isolated stellar mass black holes, those dark remnants of massive stars that roam the galaxy silently. It has revealed a population of rogue planets, worlds untethered to any star, cast adrift in the interstellar darkness. Each brief flash in the data is a story of a hidden object briefly revealing its presence through the pure geometry of gravity, a ghost writing its name in borrowed light before vanishing back into the eternal night. The ghostly arcs and fleeting flashes are undeniable, but what exactly are they revealing? The profound answer is that gravitational lensing is our only tool for mapping a substance that forms the universe's hidden architecture, a substance we call dark matter. For decades, the evidence for its existence has been building from multiple, independent lines of inquiry, all pointing to the same unsettling conclusion. The first major clue came from the way galaxies spin. Stars orbit the center of a spiral galaxy like our Milky Way, and according to the laws of gravity, those stars on the outer edges, far from the luminous core, should move slower, just as Pluto orbits our Sun more slowly than Earth. Yet when astronomers measured these rotation speeds, they found something astonishing. The outer stars were whipping around just as fast as the inner ones. The visible mass of stars and gas was nowhere near enough gravity to hold these speeding stars in their orbits. The only explanation was that each galaxy is embedded within a vast, spherical halo of something invisible, providing the extra gravitational glue. This missing mass was the first hint of dark matter. A second clue came from observing entire clusters of galaxies. These are the largest gravitationally bound structures in the universe, with hundreds of galaxies swarming like bees. When we measure the speeds of individual galaxies within a cluster, we find they are moving so incredibly fast that the cluster should have torn itself apart long ago. The combined gravity of all the visible galaxies is far too weak to hold the cluster together. Again, an immense amount of unseen mass must be present, binding the entire structure, a hidden skeleton holding the cosmic city in place. The final, and perhaps most compelling, evidence comes from the afterglow of the Big Bang itself, the cosmic microwave background. The subtle patterns in this ancient light are a frozen record of the universe's infancy, and they tell us precisely how much total matter exists. The staggering result is that all the atoms making up every star, planet, and galaxy account for only about 15% of the total matter. The other 85% is something else entirely, a form of matter that does not interact with light, known as non-baryonic or dark matter. This is the invisible cosmic structure. It is not made of the protons, neutrons, and electrons we know. It is a different kind of substance, woven through and around every galaxy, every cluster, forming a vast, shadowy web upon which the luminous universe is built. And because it only interacts through gravity, it is perfectly invisible to every traditional telescope. This is why gravitational lensing is not just another tool, it is our only direct line of sight. We cannot see the dark matter, but we can see how its immense gravity warps the light from everything behind it. Every distorted galaxy, every Einstein ring, is a point on a map we are only just beginning to draw, a map of the true, hidden foundation of reality. Gravitational lensing gave us the map, but to read it, we first needed a cosmic scale. The very first, and perhaps most startling, thing this new tool revealed was the true weight of the universe's grandest cities, the galaxy clusters. Before lensing, astronomers could only estimate a cluster's mass by adding up what they could see, the combined light of billions of stars and the glow of hot gas. It was like trying to guess the weight of a mountain by only measuring the trees on its slopes. The results were always unsettlingly light, completely insufficient to explain the violent motions of the galaxies within them. Then came the lenses. Clusters like Abell 1689, a sprawling metropolis of galaxies billions of light-years away, became the perfect laboratories. In its deep images, we do not just see the cluster's own galaxies. We see a spectacular tapestry of warped light behind it, dozens of stretched and smeared arcs, each one a distant galaxy grotesquely magnified. The geometry of these arcs is the key. Just as the shape of a shadow tells you about the object casting it, the precise curvature and placement of these lensed arcs reveal the shape and depth of the cluster's gravitational well. By meticulously reverse engineering the light's journey, astronomers can calculate exactly how much mass is required to bend it that way. They can create a detailed mass map, pinpointing where gravity is strongest. The answer is always the same. The visible galaxies, the very things that give the cluster its name, account for only a tiny fraction of the total weight. The overwhelming majority of the mass, the true gravitational anchor of the entire structure, is invisible. It forms a vast, smooth cloud that permeates the entire cluster, holding the speeding galaxies in its grasp. This was the first direct quantitative proof that dark matter was not a minor component, but the dominant substance of the cosmos. The most dramatic evidence of all came from a cosmic collision known as the Bullet Cluster. Here, two giant galaxy clusters have recently smashed through one another at unimaginable speed. In this wreckage, the different components of the universe behaved in revealing ways. The hot gas, the normal matter that fills the space between galaxies, was slowed by friction and piled up in the collision's center, glowing brightly in X-rays. But the galaxies themselves, and more importantly the invisible mass mapped by gravitational lensing, sailed right through the collision almost unaffected. The lensing map showed two distinct peaks of mass, ghostly halos that had become separated from the visible gas. This was a cosmic dissection, proving that most of the mass does not interact with light or even with itself, it simply feels gravity. The dark matter had been caught in the act, revealing its nature through its sheer indifference. For the first time, we could not just infer dark matter's existence. We could point to its exact location and measure its staggering abundance, proving that the universe we see is just the decorative trim on a hidden, massive frame. The Bullet Cluster is not just a pretty picture in a telescope. It is a cosmic crime scene, and gravitational lensing provided the definitive evidence. Here, two immense families of galaxies, each containing hundreds of members, have violently collided and passed right through one another at speeds of millions of miles per hour. This catastrophic event performed a natural experiment, separating the universe's ingredients by their fundamental properties. The first ingredient is the hot gas that fills the space between galaxies, the normal, atomic matter we understand. As the clusters collided, this gas cloud slammed into itself. Particles interacted, creating friction, and the entire luminous mass piled up and slowed down in the center of the wreckage, glowing fiercely in X-ray light that our satellites can detect. It behaves exactly as normal matter should, but the other components told a different story. The galaxies themselves, vast islands of stars, are so far apart that they sailed past one another like swarms of bees, largely unaffected. More importantly, the true mass of the clusters, mapped with exquisite precision by measuring the subtle gravitational lensing of background galaxies, did something extraordinary. The map revealed two distinct, massive blobs. These were the invisible dark matter halos of the original clusters, and they had simply passed through the collision and each other, continuing on their way as if nothing had happened. They did not slow down, they did not pile up with the gas. This separation is the smoking gun. It proves that the dominant form of matter in the universe does not interact with light or with itself in any way except through gravity. It is collisionless. If dark matter were simply a modification of the laws of gravity, the effect would not have separated from the normal matter, it would have stayed with the gas. The lensing map showed us the ghost, and the ghost walked right through a wall. This single observation provided the most direct empirical evidence we have that dark matter is real. It is something physical, and it is fundamentally different from anything made of atoms. It is the shadow skeleton of the cosmos, revealed only when the universe itself performed a brutal, revealing test. The story does not end with colossal galaxy clusters. To truly understand the dark universe, we must zoom in from the sprawling cosmic cities down to a single, solitary home of stars. Our own Milky Way is not just a disk of light, it is a sphere of influence, a kingdom defined by an unseen monarch. This is where the subtle power of weak gravitational lensing performs its most delicate work, mapping the dark matter halo of an individual galaxy. The principle is the same, but the scale is intimate, and the signal is a whisper among whispers. Picture a large spiral galaxy like our neighbor Andromeda as the foreground lens. Now imagine the tapestry of countless, much more distant galaxies spread across the sky behind it. As their light journeys toward us, it must pass through the outskirts of Andromeda's immense gravitational field, the halo of dark matter that extends far beyond its glittering spiral arms. Each photon is deflected by a minuscule, immeasurable amount. No single background galaxy appears warped to our eyes, but by studying the shapes of tens of thousands of these faint galaxies that appear to surround Andromeda in the sky, astronomers can detect a pattern. There is a coherent, statistical tendency for their shapes to be very slightly stretched in a direction that curves around the foreground galaxy. It is an exquisitely subtle signal, like detecting the gentle pressure of a breeze by watching the way a field of grass all leans in the same direction. This collective, radial stretching is the fingerprint of the dark matter halo. By measuring its strength and how it changes with distance from the galaxy's bright center, we can chart the halo's profile. We can weigh it. The results are consistently profound. For a typical spiral galaxy, the visible disk of stars and gas, the part we see in photographs, is merely the jewel in the center of a vast, invisible crown. The dark matter halo is often 10 times larger in diameter and contains over 10 times more mass than all the stars, planets, and gas combined. It is also shaped differently. The luminous galaxy is a flat, spinning pancake, but the dark matter halo is a roughly spherical cloud, enveloping the entire system in a gravitational embrace. This defines the true size and shape of a galaxy. The stars are just the bright, dense core of something far greater and mostly unseen. When we look at the Andromeda galaxy, we are not seeing its boundaries, we are only seeing its glowing heart. Its true territory, ruled by dark matter, stretches across hundreds of thousands of light years of otherwise empty space, a hidden empire whose borders are written only in the bent paths of distant light. These individual halos, however, are not isolated islands. They are knots in a grander tapestry, connected by threads of darkness that span the unimaginable voids between galaxies. This is the cosmic web, the largest structure in the universe, and its primary building material is the very substance we cannot see. To map this architecture of emptiness, we must pull our lens back, far back, until entire clusters of galaxies shrink to mere points of light. This is the ultimate ambition of weak gravitational lensing, to conduct a mass census of the cosmos. Instead of focusing on a single galaxy or cluster, astronomers now point their most powerful telescopes at enormous, blank patches of sky, areas seemingly devoid of prominent features. They capture the deepest, widest images possible, collecting the faint light from tens of millions of the most distant galaxies. Each one of these galaxies is a tiny, backlit pinprick, and each one's light has traversed billions of light years of expanding space, passing through the gentle gravitational hills and valleys of the large-scale cosmic web. The distortion inflicted upon any single galaxy is vanishingly small, completely lost in its own irregular shape. But with millions of data points, a pattern emerges from the noise. By measuring the subtle, coherent alignments in the shapes of all these background galaxies, scientists can construct a three-dimensional mass map of everything that lies between them and us. It is like using a billion distant candles to cast the shadow of a vast, intricate sculpture. What emerges from this statistical whisper is a revelation, a ghostly skeleton. The map shows that dark matter is not smoothly spread like a fog. It is concentrated into a vast, interconnected network. Dense knots appear where massive galaxy clusters reside. From these knots, faint, tendril-like bridges of mass stretch out, connecting to other knots in a complex, three-dimensional lattice. These are the filaments of the cosmic web, highways of dark matter along which normal matter flowed in the early universe to form the galaxies we see today. The luminous galaxies and clusters we catalogue are merely the glittering ornaments hanging at the intersections of this dark framework. This observed web, painstakingly pieced together from the warped light of countless galaxies, matches with stunning fidelity the predictions of our most advanced supercomputer simulations of cosmic evolution. Those simulations start with the faint ripples of the Big Bang and, driven by the relentless pull of gravity, evolve over billions of virtual years. They consistently produce a universe structured as a web, a cosmic spider's silk spun from dark matter. The fact that our real-world lensing maps see this exact structure is a triumphant confirmation that our understanding of the universe's growth, from its smooth infancy to its clumpy present, is fundamentally correct. We are not just theorizing about the web, we are now tracing its filaments with light bent by their invisible mass, drawing the blueprint of all creation. Mapping the cosmic web reveals the universe's grand architecture, but to truly understand dark matter, we must peer into its very grain. The detailed structure within those vast halos and filaments holds the key to its fundamental nature. After all, dark matter is not just a placeholder in our equations, it must be made of something. Physicists have proposed many candidates, from exotic particles that move sluggishly to ones that stream through space at near light speed. The problem is, these hypothetical particles would sculpt the universe in subtly different ways, especially on the smallest scales. This is where gravitational lensing becomes more than a map maker. It transforms into a particle physics laboratory of cosmic proportions. Think of it this way: if dark matter is made of heavy, slow-moving particles, often called cold dark matter, it would clump together easily from the universe's earliest moments. Our most sophisticated simulations predict that this model should produce halos filled with a rich substructure, like a matryoshka doll of darkness. A large galaxy's halo should be littered with thousands of smaller subhalos, the remnants of smaller clumps that were swallowed during the galaxy's growth. Many of these subhalos would be completely dark, hosting no stars at all, just pure, concentrated packets of the invisible substance. On the other hand, if dark matter is warmer, made of lighter, faster-moving particles, it would have streamed smoothly across larger distances in the early universe, wiping out many of those smallest clumps. A warm dark matter universe would have far fewer of these tiny, dark satellites. So how do we count something we cannot see? We use gravitational lensing's exquisite sensitivity to hunt for these missing clumps. The method is ingenious. Astronomers study the light from a distant, compact source like a quasar, lensed by a foreground galaxy. They create a precise model of the galaxy's main halo to predict how the quasar's multiple images should appear. But sometimes the observed images are slightly brighter or positioned in ways the smooth model cannot explain. The best explanation is that the light rays have passed near an invisible subhalo, a small knot of dark matter within the larger halo. This tiny extra warp acts like a hidden lens within a lens, leaving a faint fingerprint on the already distorted light. Each detection or telling absence of these gravitational anomalies constrains what dark matter can be. Finding numerous small-scale clumps supports the cold dark matter model that has long been our leading theory. A lack of such clumps would point toward warmer, more exotic possibilities. It is a cosmic game of hide and seek where the hidden objects are knots of an unknown particle, and the only way to seek them is by watching how they bend the light from a beacon billions of years away. With every anomalous flicker in a lensed image, we are not just mapping mass, we are beginning to feel the texture of the universe's hidden fabric, one invisible particle at a time. This search for dark matter's texture is a quest for the present, but gravitational lensing also grants us a second, equally profound gift, a window into the deepest past. By bending light, it does more than reveal hidden mass. It acts as the universe's own magnifying glass, bringing into focus objects so distant and faint they would otherwise be forever beyond our sight. This is the power of strong lensing as a natural telescope, and it has revolutionized our view of the cosmic dawn. When a massive galaxy cluster warps spacetime, it does not just distort the images of background galaxies, it amplifies their light. Think of how the curved base of a wine glass can concentrate sunlight into a bright spot. In the same way, the gravitational dimple of a cluster focuses the feeble light from galaxies at the very edge of the observable universe. The magnification can be enormous, sometimes boosting the brightness of a distant object by a factor of 10, 50, or even more. This amplification is what turns the impossible into the observable. Without this cosmic assist, the first generations of galaxies are little more than faint, reddish smudges, their light stretched and dimmed by billions of years of cosmic expansion. Their signals are lost in the noise, too weak for even our most powerful telescopes like Hubble or James Webb to detect on their own. But when one of these primordial galaxies lies directly behind a massive foreground cluster, its light is caught and focused. The cluster's gravity effectively builds for us a telescope lens thousands of light years across, a piece of optical engineering no human project could ever construct. Through these natural lenses, we have discovered galaxies from when the universe was only a few 100 million years old, mere infants in cosmic terms. We see them not as they are today, but as they were when their light first began its journey, a journey that was serendipitously steered and brightened by an invisible hand halfway home. These are not just distant objects, they are time capsules, their amplified light carrying chemical signatures that tell us about the earliest episodes of star formation, before many of the heavy elements that make up our world even existed. Each magnified speck is a direct glimpse into the era of first light, when the dark ages of the universe were ending and the first stellar fires were beginning to ignite. By using these gravitational telescopes, we are not just pushing the observational frontier, we are catching the universe in the act of building itself, watching the very first pieces of the luminous cosmic web switch on, one magnified galaxy at a time. But perhaps the most profound measurement we can make with a gravitational lens is not of an object but of time itself. When a lens creates multiple images of a single, flickering quasar, it does more than just bend light. It creates a cosmic hall of mirrors where each reflection arrives at a different moment. This is because the light for each image takes a physically different path around the lens. One path might be slightly longer, or it might travel through a deeper part of the gravitational well, where time itself slows down according to general relativity. The result is a time delay. Imagine a single flash from that distant quasar. The light racing out along the shorter, faster path reaches our telescope first, creating a bright pulse in one image. Days, weeks, or even months later, the light that took the longer, more warped route finally arrives, creating the same pulse in a second image of the exact same quasar. By patiently monitoring these lensed quasars for years, astronomers can measure this delay with exquisite precision. They watch for the characteristic flicker pattern to repeat itself in the second image, like a distant echo. This measured delay is a golden piece of information. When combined with a detailed model of the lens's mass distribution, which we get from the image's positions and distortions, it allows us to perform a remarkable calculation. We can essentially use the geometry of the lens as a cosmic rangefinder to measure the absolute distance to the quasar and to the lens itself, and distance in an expanding universe is the key to its expansion rate. This technique is called time delay cosmography, and it provides one of the most direct, independent methods for measuring the Hubble constant, the number that tells us how fast the universe is expanding today. This measurement is crucial because right now, cosmology faces a significant puzzle. Two different, highly trusted methods for measuring the Hubble constant disagree. Measurements based on the ancient cosmic microwave background suggest one expansion rate, while measurements using nearby supernova and stars suggest a faster one. This discrepancy, known as the Hubble tension, could be a hint of new physics, a sign that our understanding of the universe's ingredients or evolution is incomplete. Time delay cosmography offers a completely independent path, using the pure geometry of warped spacetime as its ruler. Each carefully monitored lensed quasar is a new data point, a new vote in this cosmic debate. The results so far are intriguing, tending to favor the faster expansion rate measured in the local universe. Every flicker we track in those mirrored images is not just a curiosity, it is a direct probe into the fundamental rhythm of the cosmos, a way to listen for the heartbeat of an expanding universe using the delayed echoes of light bent by invisible mass. That same flicker of a distant star, brightened by a passing cosmic lens, can carry an even more exciting secret. Sometimes the light curve, the graph of that star's brightening and fading, does something unexpected. After rising smoothly to a peak, it might show a tiny, symmetrical bump, a brief extra flash superimposed on the main event. This subtle blip is the signature of a world. It means the object acting as the gravitational lens is not alone. It is a star, and orbiting that star is a planet. Here is how it works. During a microlensing event, the foreground star's gravity creates a small, magnifying region in space. If that star has a planet, the planet's own much smaller gravity creates its own, even tinier magnification region. As the star and planet move together across our line of sight to the background star, the background star's light is primarily magnified by the host star. But if the alignment is exquisitely precise, the background star will also pass through the planet's minute gravitational zone. For a few hours or days, the planet adds its own tiny focusing power to the mix, creating that distinct secondary bump in the light. It is a whisper within a whisper. This method possesses unique, almost magical advantages because it relies on gravity, not light. It can find planets orbiting at tremendous distances from their stars, worlds so far out they receive almost no stellar warmth, lurking in the perpetual twilight of their solar system's outer reaches. These are planets' other detection methods, which look for a star's wobble or a periodic dimming as a planet transits, often miss entirely. Even more remarkably, microlensing can detect planets that belong to no star at all. If the lensing object is one of these solitary, free-floating worlds, its passage will create its own, much fainter microlensing flash, a lonely signal from a rogue planet drifting through the interstellar dark. Each of these events, whether a bump on a curve or a solitary pulse, adds a data point to a galactic census. Microlensing is not about studying individual planetary systems in detail. It is about taking a statistical survey of the galaxy's total planetary population. It tells us how common these distant, cold, or orphaned worlds are, revealing a hidden demographic of planets that complete our understanding of cosmic architecture. The universe is not just filled with stars and dark matter, it is also teeming with worlds, and some of them we can only find by watching for the way their silent gravity briefly bends a single, far-away point of light. Detecting that universal whisper is a staggering technical feat. The signal weak lensing seeks is almost impossibly small. The typical distortion it imposes on a distant galaxy's shape is less than 1%, a change far slighter than the width of a single human hair seen from across a football field. To find this infinitesimal shift, astronomers must overcome a cacophony of cosmic and terrestrial noise. The first hurdle is our own atmosphere. The air above us is turbulent, constantly shifting and blurring the light from stars, a phenomenon that makes stars twinkle. For precise shape measurements, this atmospheric shimmer is a disaster, smearing the delicate outlines of galaxies into fuzzy blobs. This is why the most ambitious weak lensing surveys rely on space telescopes like Hubble and the Euclid Observatory, which operate in the crystal-clear silence above Earth's air. But even with a perfect view from space, the tools themselves introduce error. No telescope mirror is flawless, and no camera sensor is perfectly uniform. Tiny imperfections in the optics can subtly stretch a star's image in one direction, mimicking the very lensing signal we are trying to detect. Before we can measure the universe's warping, we must first understand and map the warping introduced by our own instruments, a painstaking process of calibration using images of dense star fields. Yet the greatest source of noise comes not from our atmosphere or our telescopes, but from the galaxies themselves. Galaxies are not neat, round dots. They are naturally irregular. Spiral galaxies have arms, ellipticals have lopsided distributions, and mergers create chaotic, twisted shapes. This intrinsic variety, known as shape noise, is millions of times stronger than the weak lensing signal. It is like trying to hear a single, quiet violin note in a stadium where every member of the crowd is shouting a different random word. The only way forward is through immense numbers and sophisticated statistics. Astronomers must collect images of not hundreds, but hundreds of millions of galaxies. For each one, advanced software meticulously analyzes its light, not as a simple blob, but as a complex distribution of pixels. It measures the galaxy's ellipticity, its orientation, and carefully subtracts the distortions caused by the telescope and atmosphere. No single measurement is trusted. Instead, across a vast patch of sky containing tens of millions of galaxies, the software searches for a statistical whisper. It looks for a coherent pattern, a tendency for galaxies in one particular area of the sky to show a very slight, shared alignment in their shapes, a gentle shearing that points around an invisible center of mass. Isolating this signal requires algorithms of immense complexity and computing power, sifting an ocean of random shapes to find the faint, coherent tide of gravity's influence. It is a testament to human ingenuity that we can now perceive a distortion so slight, using it to trace the outline of darkness across billions of light years. The hunt for this cosmic whisper is about to receive a revolutionary new tool. On a remote mountaintop in Chile, a facility is being completed that will transform our view of the universe more profoundly than any telescope before it. The Vera C. Rubin Observatory is not just another telescope, it is a cosmic census machine, engineered to perform one of the most ambitious scientific projects in history, the Legacy Survey of Space and Time. Its mission is staggering in scale. Over the course of a decade, its massive mirror and enormous digital camera, the largest ever built, will scan the entire southern sky every few nights. It will not just take a picture, it will create a continuous, ultra-high-definition movie of the cosmos, capturing the light of billions of galaxies each night and returning to image them again and again. This relentless repetition is the key. By observing the same patch of sky hundreds of times, the survey will peer deeper than ever before, revealing the faintest, most distant galaxies. But more importantly, it will track change. It will catch the flicker of supernova, the subtle shifts of asteroids, and the variable glow of distant quasars. For the study of gravitational lensing, this data will be a goldmine of unprecedented richness. The sheer volume of galaxies it will catalog, an estimated 20 billion, is beyond comprehension. This vast number is what will finally tame the noise. Remember, weak lensing relies on finding a coherent signal in the random shapes of millions of galaxies. With only millions of galaxies, the statistical signal is faint, like trying to predict an election by polling a single neighborhood. But with tens of billions of galaxies, the statistics become overwhelming and precise, like polling an entire nation. The Legacy Survey of Space and Time will provide that national poll for the cosmos. It will allow scientists to create weak lensing mass maps with a detail and accuracy we can barely imagine today, charting the dark matter web across a third of the sky and back through billions of years of cosmic time. This will not just be a static map, it will be a time-lapse film of the universe's hidden skeleton as it grows and evolves. By measuring how the Webb structure has changed over the last several billion years, we will put dark energy, the mysterious force accelerating the universe's expansion, under the microscope. Does the strength of dark energy change over time? How exactly does it oppose the relentless pull of gravity that builds the cosmic web? The subtle differences in the lensing maps across different cosmic epochs will hold the answers. The Vera C. Rubin Observatory is poised to turn the faint whisper of warped light into a clear, commanding voice, one that may finally tell us what the dark universe is truly made of. Mountaintop observatories peer through a turbulent ocean of air, but to see the universe with perfect clarity, we must rise above it. Space telescopes offer a view unblurred by our atmosphere, and for the delicate art of gravitational lensing, this pristine vision is transformative. Each great observatory in orbit brings a unique strength to this cosmic detective work, forming a complementary team that spans decades of discovery. The Hubble Space Telescope, launched in 1990, became the first to show us the true beauty and power of strong lensing. Free from atmospheric shimmer, its sharp optics captured galaxy clusters with breathtaking detail, revealing those spectacular arcs and Einstein rings not as fuzzy suggestions, but as crisp, undeniable features. Hubble's deep field images, staring for days at seemingly empty patches of sky, were often filled with these graceful warps of light, proving that lensing was not a rare curiosity but a fundamental feature of the cosmos. It provided the first high-resolution mass maps of clusters, turning them from smudges of light into detailed laboratories for studying dark matter. Yet Hubble, for all its power, primarily sees in optical and ultraviolet light. To peer back to the very first galaxies, we need to see in infrared, as the expansion of the universe has stretched their ancient light far beyond the red end of the visible spectrum. This is the revolutionary domain of the James Webb Space Telescope. Webb's giant gold-coated mirror and sensitive infrared instruments are perfectly suited to study the most distant objects magnified by gravitational lenses. Where Hubble might see a faint red arc, Webb can dissect its light, revealing the chemical composition and structure of these infant galaxies. It sees through the cosmic dust that shrouds early star formation, allowing us to witness the building blocks of the universe being assembled in the intense gravitational focus of a foreground cluster. Webb uses these natural telescopes to look further back in time than ever before, observing the era when the first stars and galaxies were switching on and beginning to illuminate the vast dark matter web. While Hubble and Webb excel at studying individual lenses and magnified objects in exquisite detail, a different kind of mission is needed to map the dark universe on the grandest scale. Enter Euclid, the European Space Agency's Cosmology spacecraft, launched in 2023. Euclid is not designed for stunning, zoomed-in portraits. Its purpose is to conduct a supremely precise, wide-angle survey of the sky. Its instruments are engineered for one primary goal: measuring the weak gravitational lensing distortion across billions of galaxies with unprecedented accuracy. From its stable vantage point a million miles from Earth, Euclid will map the shape and distribution of over a third of the sky, creating a three-dimensional chart of the cosmic web's dark matter skeleton and tracing the influence of dark energy across 10 billion years of cosmic history. Together, this fleet of eyes in the sky forms a perfect alliance. Hubble gave us the proof and the beauty. Webb uses that magnifying power to explore the deepest past. And Euclid will provide the definitive statistical map, the grand census of the hidden universe. From the detailed portrait to the widest panorama, they are teaching us to see with gravity's own eyes. Even with a fleet of telescopes, the map we draw is never perfectly sharp. Gravitational lensing is a powerful tool, but it is not a magic wand. It comes with its own set of profound puzzles and limitations, challenges that astronomers must solve to ensure the whispers they hear are truly from the cosmos and not from their own instruments. One of the most stubborn problems is known as the mass sheet degeneracy. It is a cosmic version of an optical illusion. Imagine you are looking at a distorted, lensed image of a distant galaxy. You can measure its warped shape and the positions of multiple images with incredible precision. But here is the catch: there is not a single, unique mass map that can produce that exact pattern. You could achieve the same observed distortion with a dense, compact clump of dark matter, or with a more spread-out halo plus a uniform, invisible sheet of mass spread across the entire field of view. It is like trying to determine the shape of a lens by looking only at the distorted image it creates. You cannot tell if the lens itself is thick in the middle or if a thin, perfectly flat piece of glass has been placed in front of it. This degeneracy means that without additional, independent clues, we cannot precisely weigh a galaxy cluster or measure the exact profile of a dark matter halo. To break this illusion, astronomers must bring in other forms of evidence. They study the motion of galaxies within the cluster, or the glow of hot X-ray gas, which traces the gravitational potential in a different way. Combining lensing with these other probes is like viewing an object with both eyes open. It provides the depth perception needed to see the true three-dimensional shape of the mass. A second major challenge lies in modeling the lens itself. To reverse engineer the path of the bent light, we must make assumptions about the distribution of mass in the foreground galaxy or cluster. We often model these halos as smooth, symmetric distributions, but the real universe is messy. Galaxies have stars, gas, and satellite galaxies, all of which can create tiny bumps and wrinkles in the gravitational landscape. If our model is too simple, if we assume perfect smoothness where there is actually lumpiness, our reconstruction of the background source and our measurement of the halo's properties can be subtly biased. It is like trying to calculate the exact shape of a funhouse mirror by assuming it is perfectly curved, when in reality it has a series of small dents and imperfections. The latest research is pushing into this complexity, using supercomputers to create ever more realistic mock universes, testing how well we can recover the truth from lensed images when we know all the gory details of the simulation. Finally, there is the monumental task of measuring galaxy shapes themselves. Remember, the weak lensing signal is a distortion of less than 1%. A galaxy's intrinsic irregularity, its spiral arms or lopsidedness, is a far stronger signal. To isolate the tiny gravitational shear, we must average over millions of galaxies, but we must also perfectly understand and subtract every other possible cause of shape distortion. The blurring of Earth's atmosphere, even when corrected, leaves residuals. The optics and sensors of the telescope introduce their own subtle shears. Even the very process of converting starlight into digital pixels can create minute biases. If the camera's pixels are not perfectly square, or if the software used to measure galaxy shapes has a slight preference for detecting certain orientations, it can mimic a lensing signal that does not exist. These systematic biases are the primary enemy of precision cosmology. The frontier of the field is no longer just about collecting more light. It is about understanding our tools and our data with obsessive precision, calibrating every conceivable error to a level never before attempted. The quest to map the dark universe is in equal parts a journey into the deepest cosmos and a masterclass in meticulous, painstaking detective work right here at home. The ultimate test of this cosmic vision lies in the oldest light we can see. Billions of years before the first stars flickered on, the infant universe glowed with a uniform, brilliant light. As space expanded, that primordial fire stretched and cooled into a faint microwave whisper that now permeates all of space, the cosmic microwave background. This ancient afterglow is our most pristine snapshot of the universe at just 380,000 years old, a baby picture of cosmic structure. But that picture did not travel to us untouched. On its journey across nearly 14 billion years, the light of the cosmic microwave background had to pass through the entire evolving cosmic web, the growing hills and valleys of dark matter and galaxies. And just like the light from distant galaxies, this first light was gently bent. The gravitational lensing of the cosmic microwave background is the most subtle effect of all, a statistical warping written into the fabric of the universe's first photograph. We cannot see individual arcs or multiple images here. Instead, the effect reveals itself as a subtle smoothing and scrambling of the background's intricate temperature patterns. The early universe was not perfectly smooth. It had tiny, random ripples of density, hot spots and cold spots imprinted from the Big Bang. These ripples create a specific, predictable pattern of hot and cold across the sky like a cosmic fingerprint. Gravitational lensing by all the matter that formed later subtly distorts that fingerprint. It smears the hot spots, blends the edges of cold spots, and introduces a characteristic statistical signature that would not exist if the light had traveled through empty, flat space. Think of it as looking at a patterned wallpaper through a pane of old, wavy glass. The pattern is still there, but its details are slightly softened and shifted by the imperfections in the glass. The pane of glass is the entire large-scale structure of the universe. By meticulously analyzing the precise statistical properties of the cosmic microwave background's temperature, and even more sensitively, its polarization, scientists can reconstruct the lensing effect. They can essentially calculate the warping map of the entire cosmos that imprinted itself on this ancient light. This provides something extraordinary, a clean, early universe tracer of the total matter distribution, completely independent of counting galaxies. Galaxy surveys are fantastic, but they rely on visible objects that formed relatively late in cosmic history, and that may not perfectly trace the underlying dark matter. The lensing of the cosmic microwave background bypasses all that. It measures the gravitational influence of all matter, light and dark, integrated along the entire line of sight back to the dawn of time. It gives us a direct measure of the lumpiness of the universe's matter content from a very early epoch, a fundamental benchmark for how structure grows. When combined with later maps from galaxy-weak lensing surveys, this early universe measurement creates a powerful timeline. It tells us how the cosmic web evolved from its faint, initial ripples seen in the cosmic microwave background into the vast, clumped network of galaxies and clusters we see today. Any discrepancy between the growth predicted from the early universe and the growth we observe later could be a crucial clue, perhaps pointing to new properties of dark matter or a shift in the nature of dark energy itself. In the faint, lensed patterns of the universe's first light, we hold a silent record of everything that ever grew in the darkness that followed. But these maps are still largely static, capturing a single moment in the universe's long history. The next leap forward will be to watch the dark universe in motion. This emerging frontier is called four-dimensional lensing, and it aims to transform our detailed mass maps into a cosmic time-lapse film. The first three dimensions are the spatial ones, the vast web of dark matter filaments and halos charted across the sky. The crucial fourth dimension is time itself. To achieve this, astronomers are combining the incredible statistical power of weak lensing surveys with increasingly precise distance measurements for billions of galaxies. This distance data comes from photometric redshifts, a technique that estimates how far away a galaxy is by analyzing its color, as the expansion of the universe stretches its light toward the red end of the spectrum. By knowing not just where a background galaxy is on the sky, but also roughly how far away it is, scientists can perform a remarkable trick. They can slice the universe into depth layers, like the layers of a geological core sample. The lensing signal from galaxies in the nearest slice reveals the dark matter closest to us. The signal from galaxies in the next slice reveals the dark matter a bit further away, and so on, back through billions of years. Stack these slices together, and you build a three-dimensional mass map of the cosmic web. Now, repeat this entire process with new, deeper surveys over the coming decade. By comparing these three-dimensional maps from different cosmic epochs, we will see the dark matter skeleton evolve. We will watch filaments thicken, watch halos grow as they merge and accrete more material, and witness the large-scale structure of reality dynamically responding to the twin engines of gravity and dark energy. This four-dimensional view will tell us not just what the dark universe is made of, but how it behaves. It will measure the growth rate of structure with unprecedented precision, offering one of the most stringent tests for our models of cosmic evolution and the nature of the mysterious force that is trying to tear it all apart. The ultimate vision, however, goes beyond light alone. We are entering the age of multi-messenger astronomy, where we observe the cosmos using different complementary signals. Gravitational lensing maps the dark matter using bent light. But what if we could overlay that map with a completely different kind of cosmic messenger? Imagine detecting the ripples in spacetime from a collision of two black holes, a gravitational wave event. If that event is lensed by a foreground galaxy cluster, its signal would also be magnified and replicated, arriving at different times. A lensed gravitational wave would provide an independent, pristine measurement of the lens's mass, free from any assumptions about light. Or consider the elusive neutrino, a ghostly particle that streams through the universe almost unaffected by matter. High-energy astrophysical neutrinos are thought to be created in the most violent environments, like the jets of active galaxies. If we could trace the origins of these neutrinos back to specific points in the sky, and then look at our lensing mass maps, we might find they are coming from regions dominated by dense knots of dark matter, potentially revealing dark matter's own interactions. By combining the gravitational map from lensed light with the space-time ripples of gravitational waves and the particle signals of neutrinos, we are building a unified, multi-messenger picture of cosmic structure. Each messenger sees the universe in a different way through a different sense. Light shows us the luminous matter. Gravitational lensing of light reveals the dark matter. Gravitational waves probe the dynamics of extreme gravity. Neutrinos offer a direct line to catastrophic events. Bringing them all together onto the same cosmic cart is how we will move from inference to certainty, from mapping the hidden skeleton to understanding the fundamental physics that governs its every move. The invisible universe is beginning to speak in many voices, and we are finally learning how to listen. Gravity has become our truest guide to the cosmos. While every other telescope collects light, gravitational lensing collects influence, tracing the invisible architecture of reality through its purest effect. This single idea has given us a unified method for mapping all matter, the bright stars and the silent dark, directly through the geometry of warped spacetime. It is the only tool that does not rely on assumptions about what something is made of, only on the undeniable fact that mass bends light. Through the spectacular arcs of strong lensing, we have moved from simply inferring dark matter to directly outlining its most concentrated clumps, weighing galaxy clusters and witnessing cosmic collisions that separate the seen from the unseen. The statistical whisper of weak lensing has let us chart the gentle hills and vast filaments of the cosmic web, creating three-dimensional maps of the dark skeleton upon which galaxies are hung. And in the fleeting flashes of microlensing, we have discovered solitary black holes and rogue planets, hidden worlds revealed only by their silent gravitational touch. Together, these techniques have done more than add new objects to a catalogue. They have fundamentally altered our perception of scale and substance. We no longer look at a galaxy and see just a disk of stars. We see the luminous tip of a vast, invisible iceberg. We no longer see empty space between clusters. We see the dark highways of the cosmic web. We can even use these natural telescopes to magnify the faintest glimmers from the infant universe, observing the first galaxies as they ignited within the dark matter framework that nurtured them. The picture that emerges is one of a universe dominated by a hidden framework, an intricate, dynamic structure that guides the formation of everything we can see. Gravitational lensing has taught us to see with gravity's eyes, transforming the cosmos from a collection of luminous islands into a single, connected, and profoundly dark tapestry. The cosmos no longer hides in plain sight. From a single prediction scribbled on a page, gravitational lensing has grown into our most powerful instrument for cosmic cartography, a method that draws the universe's true blueprint in the language of bent light. It solves the original mystery not by making dark matter glow, but by making its immense gravitational presence undeniable, mapping its contours with the same certainty we once reserved for stars. This tool has moved cosmology from inference to observation, transforming our questions from does it exist to how does it behave. Every distorted galaxy and Einstein ring is a data point in a new kind of physics, one written in gravity's own hand. The journey ahead is even more thrilling. The flood of data from next-generation observatories will not just refine our maps, it will rigorously test the bedrock of our cosmic models. We will watch the dark web evolve in 4 dimensions, confront the Hubble tension with pure geometry, and perhaps finally glimpse the particle nature of the hidden universe itself. This story is still being written with every new survey and every flicker of lensed light. To follow its next chapters is to witness a fundamental shift in human perception, as we learn to see the universe not just for what shines, but for what truly holds it together. Stay curious and watch the sky. The invisible is about to reveal itself in ways we are only beginning to understand.